Captivated, I say it, I'm on a whole new intrigue. My space invaded, upgraded, I hear you talking to me. It's in the boom of the thunder, it's in the cool of the rain. And I'll say, I don't ever wanna get away. Tonight is beautiful, it's got my mind on you. And everywhere I turn is a reminder. I see you in everything, all day. And every beat of my heart keeps reminding me. I see you in every little thing, all day. No matter where I go, I know your love is finding me. I see you in everything. You're all up in everything. My soul's awakened, I'm taken by all the beauty you bring. You got it blaring, I'm staring, love watching you do your thing. There's no mistaking your style, no mistaking your touch. I see the grand, I see the subtle of your love. Lord, I see you in everything, all day. And every beat of my heart keeps reminding me. It's the final countdown. We're leaving together. Final countdown. When all this is said, it's the final countdown. Whoa,
enjoy a concert hall like that, and everyone in a classroom will be really excited. Oh my God, this is the final countdown. Final is coming up. We are so excited, right? But ever since I teach a class, I know it's never happening. And but today is indeed the last lecture of CSE142, and today we are going to give you a different perspective in computer architecture. And this is what? This is a tree, right? And most of the time when we are learning, we used to just see the tree. But if you take a different perspective, you're going to see the forest, right? And this is like a very old analogy, and I don't like that, right? And the other thing is that those photos are actually taken by others. So I like to use my photos so that I don't need to pay the license fee. So how many of you know where is that? Yeah, it's Japan, right? So it's Fujisan, right? Yeah, I like to travel to Japan every year. I'm still thinking about this year, but very likely I'm going. And so this is Fujisan, and people would say, it's so, if you are seeing Fujisan like this clear, it's very lucky for you, right? But, if you are able to take an airplane, that's the Fujisan that I could see, like 36 degrees, all right, 360 degrees, right? And, well, if you are not familiar with Japan, right, some of you have been to Seattle, so can you tell me what's that? Mount Rainier, right? And, well, again, given the weather in Seattle, it's very difficult to clearly see Mount Rainier like this, right? I've been to Seattle many times. That's one of the very few days that I can see Mount Rainier this clear. But, you know, this is the Mount Rainier that I saw on the airplane, right? So sometimes things could be crystal clear if you take a 10,000 feet from where you were located. And most of the time, when we learn things, we are digging into too much of the detail, but forget about the big picture, right? So that's why I think today we are trying to give you an overview of the class again from the beginning of the quarter to the very end of the quarters. And so when you try to review your stuff, you can start to figure out, oh, why are we learning this and why this is so important? So, you know, big picture, right? We haven't saw this a lot these days. We didn't see this a lot these days, but because I know you are tired about it. But if you want to take a 10,000 feet of all the computers, every computer is pretty much like the von Neumann architecture described here, right? So first of all, you have processor, you have memory, and most of the time we also have persistent storage, although persistent storage is not part of the von Neumann architecture by default. But it's hard to imagine that you don't store the basic code in the very beginning in the persistent storage. So some of you might be saying that I do have a computer that doesn't have a persistent storage. But don't forget, even for that kind of computer, you still have a BIOS-like ROM, right, which allow you to boot up your system, right? So I don't know how many of you have done that kind of experiments in high school, right? But you have a controller and you have a small pieces of the ROM, which stores some basic code, right? And so that's still a type of persistent storage. So that's why I always put persistent storage in a picture of von Neumann architecture. So when you want to execute a program, no matter where the program is from. So nowadays, the program can be either from the persistent storage or it's from the network. But no matter what you are executing, a program is basically a combination of a set of instructions and some data for you to begin with. And if you want to execute a program, your system must have the data and the instructions that this program needs to present it in a memory space that your processor can fetch instructions from the memory locations. And so every time when we talk about PC program counter, it's nothing but the address of the current or the upcoming instruction in the memory. And this memory is nothing else but the memory that we put in a big picture here. So that's why every time when we do this latency evaluation, I always remind you, don't forget, instruction fetch also has to access memory. So that's why a lot of you were asking, why do I have to add this 100% times whatever cycle here? Because every instruction is essentially coming from the memory by default. So after we fetch the instruction, that's the time we can start looking into the detail of the instruction. And according to what the instruction wants us to do, maybe we need to access data memory, right? So that's why data access is actually optional for every instruction. However, instruction memory access, that's unavoidable, right? And after you are done with an instruction, you can update your program counter, which would allow your processor to fetch different instructions. And then your computer will perform different functions. So some of you might be asking why the von Neumann architecture is lasting so long. Because with this concept, the hardware components doesn't need to change. What you really need to change is the memory content. So if you give the memory different content, it could be a different function, which is a different software you run on top of it. So for example, your laptop, it could be a working machine for you to perform your daily task, but it could also be a gaming machine for you, right? And most of the time, nowadays, you probably use it as a multimedia machine that you watch YouTube, for you to watch YouTube, right? So, but it's all the same machine. And why we can use the same machine for so many different things, it's just because the von Neumann architecture enables that potential. You put different content in the memory, and the processor still does the same thing, fetch, execution, but it will be completely different, right? And if you hear that's the process of executing a program, it's not too difficult for you to imagine. These are the very basic things that during an execution that you need to do. First, fetch the instruction from the memory. And then you have to decode the instruction, which means that you are going to see what the instruction really want us to do and try to prepare the register values that will be inputs for the next stage of the execution, which is really using the ALUs or generate the address or perform conditional branches for the outcome to fulfill what the instruction really want you to do. And for memory instructions, it's more complicated because you not only need to access the memory, you also need ALU operations to calculate the effective memory address for you to access. So that's why there is an additional stage for data access. However, that's optional for many, many instructions. And in fact, on average, less than half of the instruction is accessed in memory. So, and also after you have done all the operations, you can definitely put everything back to the memory. But as many of you know, memory is really slow. And your ALUs can only directly operate with registers. So most of the time, we want to keep intermediate result from the previous instruction in a register. So that's why we have the stage called write back, which is temporarily present your execution result in a certain place that's on your processor. So you don't have to always go to memory for the upcoming operations. And once you have done that, right, if you don't update your PC, you will stay at the same instructions again and again. So that's why one of the very last stage would be update the PC. However, there are two ways we might be update the PC. One is directly go to the next instruction. Most of the time, you might want to do that. And however, there's also cases where you want to change the control flow. For example, you have an if-else statement. You have a loop that you want to reuse the same code or you want to jump to different portion of the code. Then that's the time you need to update the PC according to the branch result, according to decide you want to go back, go forward, or stay at the same flow. So that's the life of execution. However, so because this is the nature how we execute instructions. So first of all, if I want to know how much time it takes to execute a program, it really depending by how many instructions within a program that we need to spend to execute the desired function. So how many of the instructions that would be part of the factor, which we typically say is IC, instructions per program, instruction count, and multiplied by how many times on average, how much time on average to execute an instructions. And that's actually determined by two factors. One is how many cycles it takes for an instruction to execute and how much time it takes for a cycle. So that's where the performance equation coming from. And also, based on the big picture, it's also not too difficult for you to imagine. These are the basic elements that we need in the processor. You need a fetch, you need a memory unit, and a memory unit would allow you to fetch instructions or access data. And you also need a program counter for you to tell where in the memory should I get my data. And also you need a unit for decoding. You need a set of register files that will provide inputs for your functional units, which including the unit of deciding the branch result, the unit of arithmetic operations, the unit for memory operations. And also, we want to know, like, okay, what are the most important pieces of program, or what's the most important pieces of the hardware, the program execution that we want to improve. So definitely you can use a lot of ways to make that analysis, but the simplest way or the most insightful way is actually MGauss law. So by MGauss law is actually written by 1/1 minus f plus f divided by s. And this f is meaning the amount of time that your target. So, and the S is by how much time I can potentially improve the targets. And with that, we learn a lot of things, but one of the most important things that guides all the software hardware development is that we want to make the common case fast. And by common case, that actually means the most time-consuming part of your program. So if we want to think about what's the most time-consuming part, it's actually memory access, first of all, right? Every instruction is coming from memory. And sometimes you also need to access data. But if you look at the speed of DRAM, it never improved since 1992 because the focus of technology is different. So turns out we start to have a performance gap between processor and memory. And this performance gap is so huge that it makes no sense for us to further improve processor performance if we cannot deal with the memory latency. So that's why our lectures start with the memory optimizations. And because two of the stages that we listed here, they have to deal with this 100 to 1,000 times longer latency. So it turns out the best solution that we found so far that give us the best trade-off between cost and performance is actually we build a memory hierarchy, which we would put multi-levels of cache in between the processor core and the DRAM. And because of that, nowadays, if your processor needs to access an instruction or a data, you only interact with your L1 cache. None of the processor core would directly access the L2 or DRAM. So, which means that you are in a totally hierarchical situation. So you can think about the hierarchy of UC San Diego. Most of the time, you won't be able to meet the principal. You won't be able to meet the chancellor because they may talk to the department chair and the department chair talk to the professor and professor talk to you, right? And so that's exactly the hierarchy, right? So if the principal wants to meet someone, right, that's pretty much, they will go through this path and it will go through you through this path. So same thing as how processor access data or instruction is that the processor would first consult L1 cache to see if the data or the instruction that we desire really locates in if it's already in the L1 cache. And if it's not there, it's the L1 cache's responsibility to look for the data or instruction. However, as you can imagine, if the L1 has very limited capacity. So most of the case, if I need to accommodate the storage of the new data block, then turns out I have to kick out some of the existing blocks using policies like LRU. And if you have completely freedom for your data to go anywhere in your cache, searching the data is really time consuming. So we try to make the L1 cache a hash-like structure. But if you only have one entry in each hash result, then turns out that you are going to have a lot of collision problems. So we try to make the cache multiple ways, or say way associativity, which is basically allowing more than one cache block resides within each hash output. So, and that hash output, each distinct hash output is considered as a set. So with that in mind, we have a lot of hardware optimization to make it efficient. But what you need to know is that even though sometimes you have sufficient amount of capacity, but because of the collision problem, because you might run out of all available slots in your hash entry, you're still going to have a miss. And if under that kind of situation, that's called a conflict miss. However, if you allow the cache block to go anywhere in your cache, but it's still going to be a miss, then that's a capacity miss. And sometimes if for the first time you brought it up, that's actually going to be a miss, then that's compulsory miss. So these are three basic types of miss, but that's a big picture of how we access cache. And the only difference between read and write is that because we want to save the time of writing. And for writing data, you have to be really careful because if you kick a block out and if you don't know which data has been modified, directly kicking out data would lead to inconsistency about your data. And in fact, your newest updates won't be able to present elsewhere. So that's why we need write back, we need dirty bit to mark what are the data that we need to take spatial care of because of that sake. So that's what happened when we, that's the difference between reading and write data. And as a software programmer, the most important thing is that you want to know the relationship between your cache access and your code. So that's why we introduced the formula of C equal to ABS, which help us to figure out if I want to mimic the method of how your cache architecture perform the hash function, as we mentioned, how am I going to partition my address to get a hash output? If I want to identify if my data is currently in a cache or not, what are the fields that I need to take care, right? So these are, so with this in mind, you will be able to figure out a code like this and see like how many of them would be miss or a hit. And surprisingly, for these pieces of code, even though we give the cache four-way set associativity, it's going to give you 100% miss rate because not only we have a lot of compulsory miss, but also because we are traversing 5 data structures at the same time. So they cause a lot of conflict misses. And through now, right, through the first round, we haven't used all stuff in a cache. So it's obviously a conflict miss. So if that's the case, you can think of how many of the following optimization might be helpful. So for example, we can change the data layout. We can change the, we can tiling our algorithm to limit the size of scope that we are visiting. You can probably think of if we are able to change the way how we structure our loop, or can we change the order of traversal, right? So those are the frequently used optimization for writing cache-friendly code. And again, right, if we go back to the life of instructions, it's okay. So in a lot of cases, right, we want the hardware to be shared among different programs. Nowadays, whenever you run a program, there must, well, whenever you launch your computer or you use your mobile phone, you must have multiple things going on, right? Otherwise, the messenger won't be able to notify you when you are browsing the web or chatting with friends. So, and the reason why we can allow multiple programs to run concurrently is also because we have the virtual memory abstraction. So the idea of virtual memory abstraction is that when you launch your program, although we said that you are going to have your program loaded into the memory, but we give one layer of abstraction called virtual memory, where when you start your program, we create an abstracted memory space called virtual memory, where your data will be virtually mapped to a unified address space where everyone sees an address space starting from 0 to the end of the defined address space. And a good thing about this address space, because it will decouple the development of software from hardware. So when you write your software, because your program is compiled using virtual address, so I don't have to care about how big the memory the machine really has. And I don't need to care about where will be the starting address of my program. On the other hand, when a system manages the software, they also have higher flexibility because they know the program is living in virtual address space. So they don't have to really care about the specific location that I need to map each virtual address space to. So that's a good thing about virtual memory. And the way how modern virtual memory system works is called demand paging and swapping. So what does that mean by demand paging? So demand paging and swapping is basically we treat the virtually created address space as the complete set, the universal set of your data and instructions. On the other hand, what does that mean is that the virtual memory is now the place where we contain everything. And the system memory is considered as a cache of your virtual memory. So what does that mean is that when processor execute a program, or two programs, right? We first create a virtual address space. And since it's cache, we don't have everything in the physical memory. What will happen is that if the program execution start to touch anything within the virtual memory unit boundary, for example, a page, that's the time we start to load stuff from the virtual memory to the physical memory. So for example, if I touch the page boundary, which you can pretty much consider a page is like a block in a cache, then we load the whole page from the virtual memory space, which is pretty much within your storage nowadays, and map it to the physical memory location when you need it. And again, since it's cache, right, we pretty much load it by the page granularity, and we only load it or unload it when we don't need it or when we need to kick it out. And gradually, of course, because your virtual memory is larger than your physical memory, and sometimes you are executing multiple programs at the same time. So it's obviously that we will have the problem that what if we run out of the physical memory? Then the solution is that you need something called swap, which is a space resides on your persistent storage to temporarily store those pages that you cannot accommodate in your system memory. So you can consider swap, which is also on storage, as where as a lower level memory hierarchy of your system memory. So that's the concept of virtual memory. However, the virtual memory, because it's an artificial abstraction created by most operating systems, so we don't actually have pretty good the native hardware support for it. And the other thing is that most of the operating systems, they like to implement their own virtual memory management mechanism. So it turns out we need to create a software-based lookup table to perform the mapping between virtual address and physical address. And the most naive way is that we just map each virtual page number to a physical page number. However, the problem with this kind of table is that it will take a lot of space. So the best way to address that is we try to think if there is more clever way of reducing the demand of address space. And turns out the opportunity is because although we have a huge virtual memory address space, but most of the time, if you look at how your program exercise on this virtual address space, we only use a beginning part and the very end part within a large virtual address space. So it turns out that if you can find a mechanism that only creates the nodes that map to the address that are in use, then we should be pretty good. So turns out the most common solution is building a hierarchical page table, which is pretty much a B tree that only contains the actual address that are in use. However, as you can see, with a B tree-like structure, you need multi-levels of memory accesses, which is already very slow in modern systems. So that's why most of the modern processors, they have the design called TLB, Translation Look Aside Buffer, which caches frequently used virtual address and physical page number mapping. However, if you place the TLB between your processor core and your L1 cache, then it's going to be slow. So that's why we start to invent another kind of abstraction, another kind of technique called virtually indexed and physically tagged cache. And the idea of virtually indexed and physically tagged cache is we try to avoid the serial access, the serialization between address lookup and your access. So what they would be able to do is that if we are careful enough to that the set index and block offset to be part of the unchanging part between your virtual and physical address mapping, that is your page offset, then we can achieve effectively the same result as using physical addresses to access your cache, but also use virtual address to look up your cache. So what happened with this is that since the set index and blocks offset, they are unchanging before and after translation. So with that, you can still partition your address with the original design, set index and block offset, and use the block offset to identify the words that you want to access, use the set index to access the set in the cache that may contain your block. However, if what we store as tag in a block is a physical address, and in the meantime, if I look up the virtual page number using my TLB, I will also get the physical address, which is pretty much the same with your tag field in your cache. Then I can still achieve the same effect as using physical address to access your memory cache and avoid a lot of issues by using virtual addresses. So that's the design of virtually indexed physically tagged cache so that we can save our access time. And however, everything has its own trade-off. So the trade-off of virtually indexed physically tagged cache is that it will limit the total capacity that you have in your L1 cache. So it turns out right now, if you look at the design of your processor, its L1 is pretty much limited by the size of your page, by the page size of your virtual memory system. And that's because every processor now is based on the virtually indexed physically tagged cache design. Okay, so with cache, with TLB, we pretty much solve our issues with slow memory. Then if you think about if the memory issue is addressed, then it comes back to the fact that can we execute an instruction more efficiently? So if you think about the original design of your processor that we use a single cycle to execute all things within a processor, that's going to be really slow. So what we want is actually a more efficient design that maintain the same throughput, but with higher rate. So what we end up doing is that we design a pipeline processor, which each cycle, an instruction only makes small amount of progress. However, when you are done with your progress, you can actually yield your resource to others. So it turns out you have shorter cycle time, but as long as you can continuously feed a new instruction every cycle, you are virtually having the same effect as a single cycle processor, but with a much shorter execution time. So that's why pipelining is a very welcoming idea that every processor is using nowadays. However, that's the ideal case. Most of the time, you won't be able to continuously fetch and execute instructions because we are going to interface a few pipeline hazards. And namely, there are three main types of pipeline hazard: the structural hazard, the control hazard, and the data hazard. The structural hazard means that if I have two stages of instructions that need to access the same hardware, the structural design, the hardware design won't allow us to do that. And the second issue is called control hazard. It's because we don't know the control flow of your program is bringing us back to the loop, forward, or jump to another location in your code, or continuous the same flow. So we have to wait until the outcome has been determined. So that's the second type of hazard. And the third type of hazard is called data hazard, which is the time that a later instruction relies on the output of an earlier instruction. However, the output is still not available in the pipeline. Then we have to wait. So that's the third type of hazard. So if you want to wait, if you are able to wait, then you can definitely solve all the issues. But a lot of cases, we don't want to wait because it's wasting a lot of time, right? So for example, like today, if I see there's a long line in Panda Express or Tapioca Express, what are you going to do? Are you going to continuously waiting, or you just go to another one, right? So the desire of go to another one or moving quickly is actually driving a lot of optimization that we are going to see. So first of all, right, as the business owner, if I really want to have more customers coming to me, then I have to solve the structural hazard by hiring more staff or giving you more locations to access. So same thing as the hardware design is that you can make more hardware resource available in your processor to avoid a structural hazard. So the most interesting thing that a lot of you were asking before the midterm is that why do I see the IL1 cache and DL1 cache when I performing my lab, and or when I do a lot of stuff that try to profile my processor? And the answer is because we want to avoid structural hazard. Thinking about the fact every cycle you need to fetch a new instruction to ensure the continuous execution of your program. However, if you have data memory access, you also need to go to memory. Then you are going to have competition between instruction fetch and data memory access. So the best way is that we just have a split instruction and data access. So that's why most of the time you are going to see a split L1 design. And the second type of optimization is on control hazard. So branch is actually one of the most frequently meet type of instructions. So in Spec 2000 benchmark programs, you will see on average, you will meet a branch every 5 instructions. And that's also true in x86 programs. So 20%, that's a very frequent chance you are going to meet a branch instruction. Can you imagine 20% of people has COVID at a time during COVID pandemic, right? So that's very common, right? So if we want to make this common case also fast, right, then we can definitely stall, but stalling is never a good idea. So what we do is that we perform branch prediction. By branch prediction, it means that we have some technique to predict the branch outcome. So what will happen is that you need to bookkeeping the branch target, which is the location when a branch is taken, where should we fetch the next instruction? And by taken, it doesn't necessarily mean your if-else statement or the statement in your while or for is true. It simply means the case where we are changing our next instruction to an instruction that is not the next instruction. So if you change the straightforward forth through path of execution to something else, for example, going back or going forward to another location that is not the next instruction, that's all considered as taken. So don't be sticky with the idea, oh, if the statement is true, it must be taken. That's not true at all, right? What is really true is that if the target, if the instruction that you are fetching is not the sequentially next instruction in the compiled order is a taken. It's a branch taken. So under what situation it must be a taken? For example, if you have a loop, and if you are continuing looping around, it's definitely require you to implement the code that going back to an earlier code. And in that case, it's definitely a taken. That's the only thing I know for sure. However, for if-else statement, depending on the compiler optimization, they may have different opinions, right? But one thing that's also important to know is that how we encode branch instruction is actually we encode the branch instruction and its target using the offset from the current branch instruction and the target instruction. So if it's going backward, then you can imagine you are going to have a negative offset. However, no matter if your offset is negative or positive, the offset would never change per instruction because it's already compiled, it's already encoded. So that's why we are allowed to have a cheat sheet called branch target buffer, which records the target address of each branch instruction. So with that cheat sheet, we don't have to go through an ALU to give us the target address of a branch. You can directly look it up. And then once you have that, you can also use a prediction result to judge how am I going to change my PC for a predicted instruction. So that's the basic idea of branch prediction. And regarding how we can make a prediction, there are many techniques. So the first technique we talk about is actually a 2-bit local predictor. So by 2-bit local predictor is a saturate counter where we have the values going from 0 to 3. And if we reach 3, no matter how many times you try to increment it, it will stay at 3. And if we are at 0, if we are decrementing it, no matter how many times you decrement the value, it will be 0. And so with that, we consider the case where the value is greater than 1, which means 2 and 3 as prediction taken. And otherwise, it's predict not taken. And whenever the actual outcome from the previous execution of the branch is taken, we increment value by 1. Otherwise, decrement it by 1. So that's how it works. And with that, we have experience for a loop like this. We get 90% accuracy, which is not bad at all. However, for cases like this, we won't be able to get 90% accuracy, but only 75%. So we try to think about if there's a better way of making prediction. And the answer is yes, because you can actually design a predictor that's called global two-level predictor, which use the history of execution regardless which branch is generating that branch outcome, to learn the pattern and use that pattern to make a prediction. And for this kind of predictor, because we make prediction regardless of each branch, and we don't maintain the states for each different branch instruction, it's called a global predictor. And it's called two-level because first of all, I have to figure out what's my history, and then I make a prediction. So that's the global predictor. And as you learned, by using a global predictor, I can reach almost 100% accuracy after I have the predictor well trained. However, we use the word trained because it's pretty similar okay, so going a little bit backward, right? So right now you hear there are different philosophies of making a prediction. A local predictor means that we are maintaining the prediction states for each different branch instruction. And by global, it means that we are making prediction based on the correlation of branches that are nearby. So these are two different philosophy of making prediction. And the number of bits simply means how many prediction states can I have. So that's the big idea behind this different predictors. And there are definitely limitations of the predictor. So for example, for this pieces of a code, which the if statement has 100%, have a 50% chance, 50% chance to be taken and not taken. And if you look at the local history of it, then it seems like, okay, it's very hard to use a too big predictor to make a perfect prediction. But if you look at the global history, then there is a case that we might be able to find out the pattern, right? So for this pieces of code, the global history predictor would do a better job. However, if I have a pieces of code like this, then even though I have the global predictor, if you want to make a perfect prediction, right, then it takes a very long history to find a pattern. So there are definitely cases that local predictor would do a better job than a global predictor. So most of the time, if you want to make a good prediction, you cannot rely on just one type of predictor. So that's why we start to have hybrid predictor like tournament predictor that combine both global and local predictor within the same thing. But before we trust either one or the other, we also have another confidence label set on each predictor to tell you which one should I trust more for different branch PC. So that's the idea of tournament predictor. Or you can consider the tournament is actually meaning the competition between two different predictors and who would win the prediction for each different PC. So that's why it's named as tournament predictor. And a lot of cases, after my introduction, you already feel like, okay, this is a machine learning problem, essentially. So 20 years ago, people have been using machine learning, perceptron, neural network method to predict the branch. And again, you just give different part of the history different weights, which is pretty much an improved version of global history predictor, but with more differentiation on which outcome should I trust or rely on more. So that's the predictor, the perceptron predictor. And in fact, all the predictors that I introduced in this class are used commercially at some point. And for now, the AMD processor and Samsung mobile phone processor, they all have the perceptron predictor at the second level of your cache. As the second level branch predictor. However, for Intel predictor, I hope I know more information, but even if I know, I don't think I can tell you. So I don't list them on the slide. But as a software programmer, it's probably less to your interest about how the branch predictor works. And in fact, what I would encourage you to do is that you should imagine that your processor already have a pretty mature branch predictor and they can make a perfect prediction if your code is really predictable. So it becomes really important, how can I make my code more predictable? And one of the earliest example that we have gave you since the very beginning of the class is this piece of code. We say, if you sort your data in the very beginning, then when I perform this threshold comparison, your performance will be better. And some of you might be thinking, why am I caring about this code pieces? And think about a select statement with a where clause that compare if an item value is greater than something. When a lot of you doing your lovely web programming or performing interaction between your customers and your company, that's a very frequently used case. So, which means, so what the code here actually implies is that if you can have your data in a sorted style, then you can actually make the program more predictable. So for this pieces of a code, it's going to be more predictable because if you don't sort your data, the best ever predictor can only achieve 50% accuracy at the best case if the data is well randomized. Do you agree with that? Right? That's the probability. So some of you were asking me about how can I figure out it's 50%. It's actually mathematical probabilistic theory tell you the best you can do is 50%, right? So on the other, so it's pretty much like a random guess, right? So and we also learned once you have a misprediction, it takes 30-ish cycles, right? Which is pretty long nowadays, right? If you already have your memory well optimized. So branch prediction, misprediction is definitely something we want to avoid. So if you can have your data sorted, so then what you can imagine is that when I have my sorted data operate on this loop, before the data reach the threshold value, everyone is probably going to be smaller than the threshold. So your branch predictor can be easily trained for that. And then after you reach the threshold, it takes a while for you to retrain the branch predictor, but shouldn't be too long according to the mechanism that we learned. So turns out you can achieve almost 100% accuracy before and after the threshold. So that's why the performance gets better. And again, we have talked about 5 different implementations, right? And we have spending a lot of time to figure out why each is better than the other. And branch actually, and a lot of compiler optimization actually plays a big part of it. So for example, for the code C and B, why C is better than B? So again, if we don't have the optimization code cache, then C is definitely going to be slower than B. However, nowadays in your processor, you already got something called cache, which make the memory access more efficient. So to do a memory lookup, you only need 1 instruction. However, for this, you not only need many instructions, but many of them also have data dependency, one after another. So that's not a good idea from C to B. And from C to D, a lot of you might be thinking, if I have a while loop, I might be able to avoid unnecessary iterations. However, that's only because you think the processor is going to implement 16 loop iteration, 16 branch instructions for that. But in fact, the compiler optimization, once we see 16, we will unroll the loop. However, if the compiler doesn't know, I must be smaller than 16. For example, if I smaller than a variable, then compiler cannot do any optimization like loop unrolling. So that's very important that if you can program in a way that you also provide hints to your compiler, then compiler can really be a very effective tool to avoid the manual optimizations. So when we say make your code more predictable, it not only has the meaning of make your code more predictable for the branch, but also for your compiler. And don't forget, hardware also have its own advanced new features. So for frequently used functions, according to Amdahl's law, hardware architects would definitely implement hardware accelerations for it. And even for the machine learning, we are seeing a lot of machine learning accelerators nowadays to accelerate matrix multiplications, convolution, or matrix vector multiplications that are used intensively in inferencing. So if it's really important for a software programmer to know if my underlying base has provided some kind of secret skill that can help me improve the performance a lot. So for the pieces of a code that we have singing is that the hardware acceleration is actually the best. Now, another kind of hazard that we haven't talked about is the data hazard. So data hazard is coming from the awkward situation where the pipeline cannot make progress because of the data dependency. And by data dependency, the only type of data dependency should affect your execution is the chance where I am still waiting for an output from an early instruction. That's the only thing should prevent you from making forward progress. However, in a lot of cases, even though we only have very few numbers of dependencies, but we still cannot make forward progress. Okay, sorry, I think I go too fast. Okay, so go back a little bit. Okay, so if you notice that, right, the potential more data dependencies means higher probability of having data hazards. So if you want to be a very efficient performance programmer, you should abandon the writing style that would create a lot of data dependencies. So for example, a lot of people would say, well, this is a very stupid way of writing swap. And they wanted to write another version of the swap. However, if you look at this swap, except for using fewer variables, which doesn't hurt, which is actually helping your performance. But if you use this kind of style of programming, the biggest issue is that you are going to see a lot of data dependencies, which potentially leads to data hazard when you execute these pieces of code, which is not great. And if your processor only know to stall, then every data dependency would essentially become a data hazard. So the hardware nowadays usually support a mechanism called data forwarding, which provide an additional data path, as we circled here, that we are allowed to make the output of any functional units to be an input of another functional unit. And with that, we are able to shorten the dependencies, the amount of stalls that we have in executing code. However, even though we do this, we still cannot avoid stalls, right? So what we are thinking is that, can we, in the meantime, can we execute instruction that has no dependency with those instructions that has dependency? And to do this, it actually requires you to have the ability of fetching and decoding more instructions at the same time, and the ability of executing more of them at the same time. So the very basic idea is called superscalar, that we just widen the instruction fetch and decode unit, and then still sequentially execute the instructions. However, with that, although there are cases that we can overlap the execution of a low latency instruction with another one. However, because we still have to wait the low latency instruction to finish to continue execution, the effect is very limited. So it turns out another thought about it is that, can we execute instructions out of order? And to know the opportunity of out of order execution, you really have to know, when am I ready to execute an instruction? So it turns out the answer is that whenever your data is ready, whenever I have a free unit, whenever the instruction, I already know what the instruction wants us to do, let me go ahead, right? So sometimes I think that maybe the best way for homework assignments and lab is that I announce everything in the very beginning of the quarter, right? So whenever you feel like I'm ready, I can start working on the assignment, I can start working on the lab. But I still didn't do it because I know everyone start working on the deadline. So but set that aside, right, for data dependency. So but okay, we have done theoretical, but after doing a theoretical study of dependency among instructions, we still figure out that a lot of cases, we cannot reorder instructions as we wish because a lot of them are sharing the same register in their input and output, even though they don't actually have the data dependency. So this kind of data dependency that shouldn't prevent you from reordering instructions are called false dependencies. And there are two types of false dependency: write after read and read write after write. So if you want to eliminate those data dependency, all you need is more registers. However, that also tells you that compiler cannot do this because compiler can only use the registers that the hardware exposed to the rest of the world. So that really comes the fact that we need a hardware mechanism called register renaming and speculative execution to make more efficient use of our functional units. So the idea of register renaming is that we provide physical registers as the temporary storage of instruction output. And whenever an instruction would generate a new output, instead of writing it to the real register, I put them in this physical registers. And these physical registers would be used as the input of a later instruction. And whenever I see a new output, I give it a new register, regardless if the architectural register, which is the name of register in the compiled code. So that's how it works. But in a case, there are also chances that we are executing your instruction on a speculative execution, meaning it's under the branch prediction. So you also need a mechanism to reclaim, recycle those incorrectly executed instructions. So our proposal is that we have a reorder buffer, which simply buffer those execution results. And if we don't present it to the rest of the world until we 100% for sure this instruction should be executed. So turns out your pipeline is going to be more complicated. You have a register renaming logic. You also have a reorder buffer. And with register renaming, if you go through a detailed process, you will figure out the execution flow is pretty much similar to draw data flow graphs like this. And with careful consideration regarding the issue with, meaning how many instructions that I can put into execution at every cycle, you will essentially get the same result as drawing a pipeline diagram as of register renaming hardware. So, and the most important message I want to deliver here, there are two things. First of all, with register renaming, you are pretty much able to execute instructions based on the data flow, data dependency. However, it also allows you to evaluate where is the most time-consuming part of my code. So if you pay attention to this code, you will figure out that each loop essentially start with the instruction of 1 plus 5n. And if you pay attention to where we start executing this 1 plus 5n instruction, you will figure out each of them is separated by 3 cycles. So you can have the idea that, okay, roughly every 3 cycles, I will be able to execute 5 instructions. So in this way, you can estimate my code has a rough CPI like 0.6. And on the other hand, it also means if I cannot shorten the 3 cycle period, there is no way I can make my performance better, the execution time shorter. So for those instructions, if you don't remove them, the execution time won't change. Those instructions are critical path instructions. So it means that if we want to improve the program performance, we really have to think about if there's ways that we can, there are ways that we can improve the critical path. And another thing is like, okay, so to avoid to shorten the critical path, you should avoid the low latency instructions to be on a data dependency chain. So one of the example is the linked list data structure. If you want to traverse it, in a lot of cases, you have to depend on a value that is stored in the memory to decide where is the next instruction to access. So it turns out there's no way that you can parallelize the lookup of your data, because without the outcome from the previous instruction, there's no way you can issue the next memory operations. So if you have a code like linked list traversal, if you cannot find a mechanism to shorten the time, there's no way that you can improve your performance. But unfortunately, if you look at the code, right, what really takes a lot of time is actually the current equal to current next, which is the core of linked list. So it gives you an idea that, okay, there is no way you can make linked list better, right? So do you really need to use this data structure, or can you be more creative, right? So those are the ways you can think about how can I make my performance better. And again, a lot of you might be curious why I don't totally rely on compiler to optimize my code. Again, compiler has no way to deal with false dependency. Okay, so again, so that's why being a programmer, you have to know what the underlying bits that I am dealing with. So the underlying bits nowadays is pretty much like this. Each processor has multiple issue pipeline, and they are essentially able to achieve a lot lower than one CPI. And even with the efficient core that we visited yesterday, it's also a 5-issue pipeline. So even the slowest core nowadays has multiple issue pipelines. So it's really important that you can write your code to issue widely. So here are the tips that I summarized that can make that happen. So first of all, can we minimize the critical path instructions operations? So to minimize the critical path, typically, who would be the critical path instructions? The memory instruction, right? If you have a cache miss, hundreds of cycles. If you have a branch misprediction, 30-ish cycles, right? So if you can reduce the chances of making branch prediction, if you can reduce the chances of making memory references, or reduce the chances of cache misses, reduce the chance of branch mispredictions, go ahead and do it, right? And to avoid that, right, we have learned tiling loop optimizations would help improving the cache performance. We already learned that sorting, loop unrolling can help improve the branches, right? And we also show you that even try to implement a lookup table would help a lot, right? And sometimes there are instructions that are really long. And in fact, like the pop count instruction itself is long. However, if the whole thing that you want to do is pop count, then it's worth doing it. But if that's not something that's mainly really important, can we try to avoid that kind of long latency instructions, right? And also, don't forget, you have a processor with multiple functional units. If there is no way for me to minimize the critical path, by any chance, can I put more instructions between along with the critical path? So not only the you still have the critical path occupying, but in the meantime, can I do something more than that, right? So that's why we have different implementations of this. And however, there are also cases that, okay, I tried my best. I still have no way to optimize my critical path instructions. I still have no way to insert more instructions along with the critical path. So then we start to have other optimization like simultaneous multi-threading, which allow us to execute multiple threads within the same pipeline to completely fill in the functional units within a single pipeline. And in this way, you can improve the throughput of executing multiple instructions. And to support simultaneous multi-threading, you need duplicated program counter. You need a wider instruction fetch unit. So your processor can create an illusion that you actually have two different processors, but that's not true. And the operating system will be deceived and then schedule 2 threads onto the same physical cores. And within the same pipeline, we still use register renaming, we still use auto order scheduling to fully utilize the pipeline. However, simultaneous multi-threading has its own drawback. First of all, because you are sharing your pipeline hardware resource with others, it definitely hurts the execution of a single thread if we don't deal with it carefully, or if we cannot create a constructive multi-threading environment. By constructive, there are also chances that if I run 2 threads in the same physical cores, that would make the performance better. So for example, if I have a thread that is running ahead of my main thread, but what if that thread can actually receive the effect of prefetching data for the other thread? That's actually helping the performance. Or as we mentioned earlier, if I have another thread instance, but turns out it will help us to train the local predictor faster than simply using one thread. You are actually creating a constructive situation that makes your branch predictor more convincing, right? So that's actually constructive. So although most of the time sharing the resource with others would make your single thread slower, there also exist cases where you can make a single a program more efficient if you do it right. And however, you also need to know there are pros and cons in SMT. So because SMT has its problem of sharing resource, so another way which is trying to maximize the area efficiency of the same hardware is called chip multiprocessor. So within the same area, with the idea of chip multiprocessor, I'm able to provide more facilities with smaller cores. And also the smaller cores, each of this, they have their exclusive resource of cache and hardware. So it turns out you are able to execute threads using those with less competition among your hardware resource. However, is that always a good thing? So you should carefully think about this question because it actually provides you a lot of space for discussion. But the answer is that there is never a clear win of simultaneous multi-threading or chip multi-threading, right? So, you know, being an adult, right? You don't want to make decision. I just want to have everything. So I take everything. So most of the time, right? The modern processor, they would have both simultaneous multi-threading and chip multi-threading, a chip multiprocessor that each core in the chip multiprocessor is also an SMT processor. So you can fully take advantage of either, right? Both. So again, right? Without software optimization, there's no way we can use multi-threaded hardware. So however, the biggest issue is that software people, they create their abstractions regardless how hardware really implements it. So it turns out the hardware has to deal with the inconsistency and incoherence of the cache content. So we have to maintain consistency and coherency. And coherency simply means that the processor would see the same data at the same time. But how we evolve the data, we have no restrictions on that. And consistency is actually even defining how the program should evolve the data. However, even with consistency and coherence protocol, through the demo we had in yesterday, right? You already learned that, well, for coherence protocol, 3 of the outputs here are theoretically possible, but most of the time we are going to see the ones that we don't want to see. That's 3 and 4, right? And also regarding performance, because we maintain states per block based, so it turns out we are going to introduce coherence means as the source C. So if you cannot write your code to better tailor for coherence needs, then you are going to interface the situation that I create an additional thread. However, my performance is actually slower than not even having the thread, which you experience a lot in your lab before. And also, okay, even though I take care of those, right? My lovely optimization in both compiler and the processor will mess up the execution of these pieces of code that all the 4 different outputs are possible, which make a lot of difficulty in debugging my code because the execution result is non-deterministic. And for software programmer, software engineer, the most difficult situation to debug is that you cannot reproduce the bug, right? So, and the reason is simply because not only the non-determinism in executing each thread, but also the compiler optimization or the processor dynamic scheduling would mess up the order of execution of instructions per thread. So turns out MFANS instruction is an architectural support for consistency. But as you can see, even with MFANS, you still cannot deal with the non-determinism in launching your thread. So turns out the MFANS instruction simply make the result more predictable, at least eliminate some of the cases, but won't be able to make your code completely deterministic. So that's why parallel programming is so hard. And a lot of us know that we have limited improvement of CPU for the sake of power. So that's why we try to look for parallelism from GPUs, which is essentially a parallel architecture based on vector processing. But for the GPU, right, you can imagine it's still a specialized hardware designed for graphics. So it has, although it has multiple ALUs that can process multiple pixels at the same time, however, because you don't actually need thousands of frames per second. So they don't actually design their ALUs to be low latency. And they don't actually need high performance branch predictors because there is no branch prediction in the code for shading, right? And also your ALU doesn't have to be really powerful because the vector instructions that we need for graphics is really simple. So a lot of you have the misunderstanding saying that GPU is the complete future, but that's actually not true because GPU is designed to be limited, right? So those are the misconceptions that we have that you should keep in mind, that don't treat GPU as the universal solution for everything. And in fact, because we have the limitation of Dinadian scaling, and that is actually limiting your GPU and CPU performance. So a lot of you might be fooled by NVIDIA. Oh, okay, sorry, be misled by some of the commercials, right? And but if you look at NVIDIA, they keep saying that, well, we can actually surpass the limitation of Moore's law. It's actually not true, right? Because if you look at the TDP of NVIDIA GPU, it's basically scaling with the number of transistors they have. So they are pretty much not dealing with the dark silicon problem. Instead, they try to put larger heat dissipation units on top of their GPUs instead of, so they are not actually dealing with the issue. They are living with the issue, right? And if you really want to deal with the issue, you have to figure out how can we lower the dynamic power or static power, right? And if you don't deal with the dynamics power and static power specifically, you are going to hit the issue called dark silicon problem that we are not able to make more heat dissipation. So it turns out that the power budget is limited. And the result is that you can either have half of your transistor on only, or you have to make everyone running slower. And if you look at that, right, that's actually fulfilling the trend that we are seeing now. So for example, nowadays processors would have more units but running slower, or that's one of the potential is like big little cores. And if you look at the GPU, it's pretty much also using slower ALUs but with more parallelism within the same chip. All right. So that's pretty much what I want to bring this up. And, thank you for the great summer session. And as I said, right, the very last thing I like to do is that I want to take a photo with you guys. So if you don't mind, we can actually take a photo together.